Welcome everybody to Algebra 2, Section 1.5, Absolute Value Equations and Inequalities. So before we do anything else on this, I want to actually first define absolute value. Absolute value, we're going to define that as, it's up here, so I'm just going to write it in absolute value. Okay. And what absolute value means is the distance from 0. And I want to really emphasize this definition because it's going to be incredibly helpful for us today as we understand this content. So absolute value, a lot of us might just think of it as making things positive. And while it does do that, that's not the actual definition, as I mentioned. The definition is the distance from 0. And that comes into play here as soon as number 1 in the warm-up. So if the absolute value of x is 7, we are saying x is, okay, so that whatever's in the absolute value is this far from 0. So x is 7 from 0 is what we're being told. And so what could be 7 from 0? Well, if we do a little bit of a number line here, zoom in here, put 0 in the middle here, and I go 1, 2, 3, 4, 5, 6, 7. Well, we notice if we go 7 to the right, 1, 2, 3, 4, 5, 6, 7, we got 7 away from 0. So if absolute value of x equals 7, what are the possible values? Well, 7 is an answer because 7 is 7 from 0. And so we're saying x is 7 from 0. However, there's another way for x to be 7 from 0, and that's for it to be at -7. And so if I just write all these in here, and I draw this across, now we see that -7 is also 7 from 0. So the possible values are both -7 and 7. They're both possible values of x. X could be either, and so we say both are solutions. Now, x can't be both at the same exact time. It would be either one or the other, but both are possible solutions. So now if we say the absolute value of x, is equal to -4, we're saying x is -4 from 0. And so the question becomes, looking at this number line up here again, is there any way for it to be -4 from 0? And the answer is no, because even the number -4 is 4 from 0. It's not -4 from 0, and that's because distance can never be negative. So there is no solution here on this one. It's impossible for it to be -4 from 0 because distance can't be negative. It's impossible. If I walk 5 steps forward and then walk 5 steps backward, I walked 10 steps. I didn't walk 0 steps because I walked -5 steps as I went backwards or something like that. Or if I drive 12 miles north and I turn around and drive 12 miles south, my car still has 24 extra miles on it than it did before. It's not like it has 0 miles because 12 miles north were positive and 12 miles south were negative, even if I were to end up in the same spot. So that's very important today as we talk about this, that absolute value is distance and distance can't be negative. So now let's talk about solving absolute value equations. So our first step is to isolate the absolute value expression. So whatever is inside the absolute value, we want to get it by itself. Sometimes this will be done for us, especially on our first few problems, and then after that we're going to notice that we are going to have to start doing that step. Step 2 is to create two cases, and that's because as we notice here, for example, there's 2 ways to be 7 from 0, and most numbers, there's 2 ways to be that far from 0. We'll see what I mean later when I talk about most numbers. But once again, most numbers, there's 2 different ways to be that far from 0. And so we have to set 2 special cases where you set the inside here. So in this case, up on number 1 in the warm-up, x would be equal to a positive version of this, the normal version of that. And then the other one is x is equal to the negative version of the other side. And so -7. Now notice I didn't change the inside at all. It didn't become positive x and negative x. Only the right-hand side changed, where one was the normal version, as it is already, and the other is the negative version of that side. And then we solve both equations here on the warm-up in number 1. That's already done for us. 7 is by itself. X is by itself. And then a good thing is to check for extraneous solutions. So let's first define what extraneous solutions. And the first 5 letters of the word extra do a lot to help us here. So these are solutions that don't work when plugged into, I should say, the original equation. So there's solutions that don't work when plugged into the original equation, but we get these extra solutions or these extraneous solutions by solving it. So sometimes when we create this second scenario here, or the first scenario even, we get an extraneous solutions. And so these, like I'm talking about, are really extra solutions. And that's a good way to think about it, is those first 5 letters of the word extraneous really help us know that these are extra solutions that aren't actually solutions that we need to get rid of and say, oh, these actually don't work. Now, the thing is you don't always have to check for extraneous solutions if you know what you're looking for. And so, these first 2 examples, I'm going to skip over that step because I'm telling you right now that it doesn't have what we're looking for. But when we get to a problem that does have what we're looking for, I will make sure to highlight that and note, hey, here's when we have to check for extraneous solutions. We didn't have to before, but when you see blank, that's when you have to check. So without further ado, let's start with number 3. So number 3, the absolute value of x minus 9 is equal to 5. So we're saying x minus 9 is 5 from 0. So some number minus 9 is 5 from 0. So our absolute value is isolated. There's not like a 5 times this or a 5 plus that or anything of that regard. Our absolute value is the only thing on this side of the equal sign. Even if x isn't isolated, the absolute value is. So we're going to go ahead and make our 2 scenarios or 2 cases. So one is x minus 9 equals this regular positive 5, and the other one is x minus 9 equals negative 5. Note again, the left side didn't change here at all. The only thing that changed was the right side became negative, and that'll always be the only change as you're doing these absolute value equations. So now solving both of these, in each equation we add 9 to both sides. On this equation on the left, that results in 14. The equation on the right results in positive 4. And so we're saying if x is 4 or 14, these are solutions. And if we were to plug them back in, if we were to plug 14 back in, for example, you end up getting the absolute value of 5 equals 5, which means 5 is 5 from 0, which is accurate. If you plug in x equals 4 back into the original, you end up getting the absolute value of negative 5 is equal to 5, which means negative 5 is 5 from 0, which once again is an accurate statement. So we'd say, yeah, okay, these are both solutions. These are true. You can always check your work just like we have been able to at plenty of other times. Next up, number 4, we have once again our absolute value isolated. So I'm going to go ahead and make my 2 cases. However, when I make them, I'm going to go ahead and put my variables in that part on the left-hand side just because we are more familiar with that. And so I want us just to be used to that. 2k plus 7 equals 3, and 2k plus 7 equals negative 3. Once again, the only thing changing is the side opposite the absolute value. There's one version that's positive, one version that's negative, but everything else remains the same. So as I mentioned, I did flip these around. If you had left 3 and negative 3 on the left side of the equal sign, that is perfectly fine as well. There's not a right or a wrong way. Most people just prefer to have it this way. So both equations, we subtract 7 and then we'll divide by 2, but the results we'll get will differ between them. So in this left equation, subtracting by 7 gives us 2k equals negative 4, and then dividing by 2 gives us k equals negative 2. The other equation, as we subtract 7, we get 2k equals negative 10, and the other one we end up getting, and then as we divide by 2, I should say, we end up getting k equals negative 5. And so even though both of these answers are negative, they are actually still solutions. Because if we were to plug negative 2 into here, we end up getting 2 times negative 2, which is negative 4 plus 7, and that's negative 3, or that's positive 3, excuse me. And 3 is 3 from 0. And if we were to plug in negative 5 in here, we end up getting negative 10 plus 7, which is negative 3. And negative 3 is also 3 from 0. So these are the two solutions, negative 2 and negative 5. And as I mentioned with compound inequalities, where some teachers are going to be very strict with those or compound inequalities of having the smaller number first, I'm not going to be strict here. So you could list these with negative 2 first or negative 5 first. You could also list them as separate ones like we did here and here and do two separate circles even, or just one big box or circle. You could also, if you wanted to, list them like k equals negative 5 comma negative 2, like that. And that would be perfectly fine as well. Now, if we were to do the list, like we see at the end, then we really do want to go least to greatest, because if we're going to go the extra mile to go and organize it that way, we want to organize it to the best of our abilities so somebody could read it very easily by going least to greatest and keeping it even more organized. Let's go ahead and go to number 5. Number 5 here, we notice the absolute value is not isolated. This plus 17 is also on that side of the equal sign, so we need to get rid of that or undo that. We would do that by subtracting 17. So I have the absolute value of y minus 1 is equal to 6. So notice the absolute value is still there. Now that my absolute value is isolated, I'm going to rewrite this in my two cases or two scenarios where I have y minus 1 equals 6 and y minus 1 equals negative 6. Once again, that right side just becoming negative on the other equation, or the side opposite the absolute value becoming negative on the other equation. So we add 1 to each side in both of these equations, and the first equation gives us 7, or the other equation gives us negative 5. And those would be our two solutions. Once again, you're able to plug these back in and check, and you would end up getting 23 equals 23 on both sides of the equation if you were to plug either one in by the time you simplify everything out. Number 6 here, 3 times the absolute value of m plus 8. So we have to get rid of this multiplication, so the absolute value will be isolated. So we divide by 3, and we end up getting the absolute value of m plus 8 equals 13. Now our absolute value is isolated, so now we can go ahead and write our two scenarios or cases. And we have m plus 8 equals 13 as well as negative 13. Beginning to solve, we subtract 8 and we get m equals 5, and we get m equals negative 21. And those would be our two answers. Number 17 here, we notice our absolute value is not by itself, so we divide by 16 to undo the multiplication, and we end up getting the absolute value of r minus 5 is equal to negative 2. We should have some alarm bells going off in our head right now. Now this is different than any other problem because we have the absolute value equal to a negative. Quick reminder, like we talked about on warm-up 2 at the beginning of this lesson, is that the absolute value is the distance from 0. And so we're saying whatever's inside the absolute value is that far from 0. So we're saying r minus 5 is negative 2 from 0. And that is not possible. So this is no solution, because you can never be a negative distance from anything, let alone a negative distance from 0. Now, if you were to have worked it out and tried solving it, I get that question all the time. Hey, what would happen if? So if you were to do r minus 5 equals negative 2, and you make another equation where the side opposite the absolute value changes sign, so positive 2, and you were to go through and solve these out by adding 5, you get r equals 3 and r equals 7. Okay. Well, if we plug these in to our original equation, we're going to notice that they actually don't work. So let's go ahead and just see this here so that way you guys can get first-hand experience now. And so we had 16 times the absolute value of 3 minus 5 equals negative 32. And we're testing this out to see if it does work. So we have 16 times the absolute value of negative 2 equals negative 32. Well, the absolute value of negative 2 is 2, and so we're going to have 16 times 2 equals negative 32, which is just incorrect. That'd equal positive 32. So we know that r equals 3 is not a solution here. And then we can test out the same exact thing with r equals 7 here, and say 16 times the absolute value of 7 minus 5 equals negative 32. And that's 16 times the absolute value of 2 equals negative 32, and you might already see where this is going. That we'll have 16 times 2 equals negative 32, which once again just is not the case. That would equal a positive 2, not a positive 32, not a negative 32. So we notice that neither of those work, which would then result in a no solution. But once again, you're best off remembering the definition of absolute value is the distance from 0, and that distance can't equal a negative. I do want to mention that if this problem had started off with a negative 16 here, instead of a positive 16, we would have divided both sides by a negative 16. And then that would lead us to the absolute value of r minus 5 equaling positive 2, and then we would have solutions. We'd have 2 solutions like we have on every problem up to this point. Because it doesn't matter whether the problem initially equals a negative, like it does up here. What matters is whether or not the absolute value equals a negative or not. So if the absolute value equals a negative, which it doesn't in this new scenario, then you get solution still. But if the absolute value equals a negative, which it does in our original scenario, then you have no solution. Moving on to number 8 here. Absolute value is not by itself, it's being divided, so we're going to multiply to undo that. We're going to multiply by negative 2 or negative 2 over 1. Do it to both sides, the negative 2's reduce. And we get the absolute value of y minus 10 is equal to 12. By the way, I should mention some tips I use for absolute value for writing it out to differentiate it from 1s or 11s or L's or any other thing we might think of it as is I write them bigger or taller than the rest of everything around it. So everything inside of it I wrote smaller than it. And I also tend to write them a little bit thicker at times as well to once again just differentiate them or set them apart from the other numbers or the actual numbers that they're containing. So now, since we have our absolute value by itself, I'm going to go ahead and split this into 2 cases. See, notice here, it equaled a negative to begin with, but now the absolute value equals a positive, so we're going to have actual answers rather than no solution answers like we did last time. So as we make our 2 equations, I'm going to start solving by adding 10, and I get y equals 22 and y equals negative 2 as our 2 solutions that once again you could plug in and they would work. Number 9 here. Once again, absolute value equals a negative to start, but as we get rid of this minus 11 by adding 11, we'll have it equal to a 6. And I'm going to go ahead and flip this around here just so I have my variables on my left and my regular number on the right. And so that's going to be the absolute value of 8 minus p equals 6. Once again, if you wanted to keep your 6 on the left-hand side, that's okay too. Now that my absolute value equals a positive, and it is by itself over here, I'm going to go ahead and make my 2 cases. Where once again, the only thing that changes is that is the side opposite the absolute value, which I always put on the right side. So now I subtract 8 from both sides and I get negative p equals negative 2 and negative p equals negative 14 in my 2 equations. And maybe you want to solve them like this, where I did now, where you do the first step in each and then the second step in each and so on and so forth. Or maybe you want to solve it like I did earlier, where you just do one equation and then the other equation. It's really a preference. Undoing this negative p, it's like a negative 1p. So you can either multiply by a negative 1 or divide by a negative 1. They accomplish the same exact results of getting our variably positive and changing the signs of the opposite side. So negative 2 becomes positive 2, and as we divide here by negative 1, we end up getting negative 14 to become positive 14 as well. And those are the 2 solutions. Number 10 here, that's new. We haven't had our absolute value equal to 0 yet. Let's see what happens. So I undo this division by multiplying by 9, or 9 over 1. And I get the absolute value of 3a plus 12 is equal to 0. Once again, that's new. Let's go ahead and try this out. So we have 3a plus 12 equals 0, and as we try to do another one, we might notice that 0 can't be negative. It's just 0. It's not positive or negative, actually. So we can't have 2 scenarios of 0. We only have 1 scenario of 0. And the reason why that is the case, so you only have one scenario, is once again, absolute value is distance from 0. And so we're saying 3a plus 12 rather, is 0 from 0. And there's only one way to be 0 from anything, and that is to be there. at that place or thing. So the only way to be 0 from 0 is at 0. The only way to be 0 from a restaurant is to be at the restaurant. The only way to be 0 from my classroom is to be in my classroom. So there's only one way to be 0 from absolutely anything, which means we're only going to get one answer when the absolute value equals 0. And like I mentioned, if you tried to write the other equation, you notice it's the exact same. And so you get the same answer twice, assuming you do your math correctly. So here I'm going to subtract 12 from both sides and get 3a equals negative 12. And then I'll divide by 3 and get a equals negative 4. And that's my one answer here. So it's the only time you'll get just one answer when it's not extraneous, which once again we're going to talk about extraneous later when they come on up, which won't come into play until we see problem number 13 is when we're going to start talking about it. Number 11 here, 9 minus 4 times the absolute value of c plus 10 equals negative 15. So I have to undo this 9 and the negative 4 multiplying. So I'm going to undo the 9 first by subtracting 9. So I get negative 4 times the absolute value of c plus 10 equals negative 24. Now as I divide both sides by negative 4, oops, yeah, I missed my second absolute value bar. I end up getting the absolute value of c plus 10 equals 6. Absolute value equals a positive or a non-negative, as it should. And so we get c plus 10 equals 6 for my one equation. My other equation is c plus 10 equals negative 6. And if you were to write this equation on the left and this equation on the right, that's okay. It doesn't matter which one's on the left or right, because regardless, we're solving them both anyways. Both equations require us to subtract 10, yielding negative 4 for the left equation and negative 16 for the right equation as our two answers. Moving on to number 12 here, negative 16 is equal to negative 12 times the absolute value of k over 5 plus 8. So subtracting 8 first, and I'm going to go ahead and flip my equation around as well. So my variables on my left-hand side, the absolute value of k over 5, negative 12 times that, negative 12 times the absolute value, is equal to negative 24 as I subtract 8 from both sides. Next, I'm going to go ahead and divide by, I don't know why I wrote parentheses, I'm going to divide by negative 12 on both sides and get k over 5, the absolute value of that, is equal to 2. And so now that I have my absolute value isolated, I'm going to make my two equations. And I get k over 5 equals 2 and k over 5 equals negative 2. Multiplying both sides by 5 over 1 yields in the first equation k equals 10. And the second equation, doing the exact same step, yields the number negative 10. Those are the two solutions. So as I mentioned a few problems ago, I said that number 13 is when we're going to first encounter the possibility of extraneous solutions. And the reason here is we have a variable there. Okay? And I'm going to talk about at the end of this problem how to check for the extraneous and whether or not it would be and when it would be. So here our absolute value is in fact isolated, and so I'm going to go ahead and start making my two equations. Now, as we mentioned, the first equation, everything stays the same, you just drop the absolute value bars. In our second equation, the only thing that changes is the side opposite the absolute value becomes the opposite signs, meaning we're changing the sign of the x, but not only the x, the 1. Both of this entire side becomes the opposite signs. So if you had 5 different things there, you're switching the sign on 5 different things. Earlier in every problem up to this point, we've only had one thing there, and so we've only changed the sign of one thing. But here, since we have two things, we'll change the sign of both. And here, they both are positive, so they'll both become negative. Now we solve each of these equations separately from each other. On the left equation, I'm going to subtract x from each side and get 2x. I'm also going to add 9 to each side and get 10. And then I'm going to divide both sides by 2 and get x equals 5. In my other one, I'm going to add x to each side to get 4x, and I'm going to add 9 to both sides to get 8. Dividing by 4 results in x equaling 2. Now, as I mentioned, we do have to check for extraneous solutions here. And what we're concerned about for extraneous solutions is the absolute value equaling a negative, if you didn't guess. The absolute value can't equal a negative, as we mentioned, because that would mean the distance is negative, and distance can't be negative. So when we plug these back in just to check for extraneous solutions, not to check if our answer was necessarily the correct answer, we did all our math right, but if we're just checking to see if something's extraneous, we only have to plug it into the side opposite the absolute value. And so if I plug in 5 here, I end up getting 5 plus 1, which is 6. That's not a negative, so it's okay. Here, as I plug in 2, I get 2 plus 1, which is 3, which once again, not a negative and is okay. If either one of those answers, or both, would have made the side opposite the absolute value negative, and thus the absolute value equal a negative, then that answer or answers would have been extraneous. So anytime an answer makes the absolute value equal a negative, it's not an actual answer, it's an extraneous answer. Moving on to 14 here, we have the absolute value being multiplied by 2. So even though there's a variable there, we're still going to go ahead and undo this multiplication by division. The absolute value of h plus 8 is equal to 7h. You just divide the numbers and leave the variable the same. So now, once again, we will write our two equations. H plus 8 equals 7h, and h plus 8 equals negative 7h. Solving these, I'm going to subtract h in each equation and get 8 equals 6h. And my other one, if I subtract h, I get 8 equals negative 8h. Dividing in both equations, dividing in the left equation by 6, results in 8 over 6, which reduces to 4 over 3, or the decimal 1.3 repeating, or the mixed number 1 1/3. My other equation, as I divide by negative 8, results in h equaling negative 1. Now, as we plug these both in, we notice, hey, the absolute value can't equal a negative, so if the absolute value were to equal a negative here, that's an issue. Well, 4/3 times 7 is a positive number, but negative 1 times 7 would be a negative number, thus making the absolute value equal a negative. So this answer is what we call, once again, extraneous. And this is our only actual answer. So if you were to, on a test or a worksheet that you turn in, circle both as actual answers and not mark one as extraneous, you would get this problem wrong. However, if you do it as I just did here, saying, hey, that second answer isn't actually an answer and that it is extraneous, you'll get this correct. Number 15 here. Once again, our absolute value is not by itself. I got to get it by itself by any means necessary. And in that case, that means adding 5n to both sides. So as I add 5n to both sides, I'm going to get the absolute value of 8 minus 2n is equal to 6n plus 2. And now I make my two equations. One where everything's the exact same except for the absolute value bars are gone. And the other one where the only change is the side opposite of the absolute value changes in signs. So positive 6n becomes negative 6n, and positive 2 becomes negative 2. Once again, you change every single sign on that opposite side. So as I solve this left equation by adding 2h to both sides, I get 8h. And if I subtract 2 from both sides to move it away from my variable, I'm going to get 6. Dividing both sides by 8 gives us the exact reciprocal of the problem of the answer on the problem we got before, and reduces to 3 over 4. My other equation, I'm going to add 6h because it's a smaller one and get 4h. So my h kind of looks like an n there. Oh wait, these are n's, and I'm writing h's. Gosh, what a silly thing I'm doing here. So let me kind of fix these the best I can to make them kind of sloppy h's there, sloppy n's there rather. That's better. So I get 4n. As I move my 8 to my other side by subtracting it, I end up getting negative 10. And dividing by 4 results in a fraction that we reduce by 2 to become n equals negative 5 over 2. So if we were to plug these both in to this point, or you could plug them up here, you just have to do more math by actually plugging it here and adding this over or subtracting it over depending on the result. Because we want to make sure the absolute value equals a positive versus equaling a negative, or potentially 0, which is fine, but the negative is not fine. So if I plug in 3/4 here, 3/4 times 6 is a positive number. I don't care what number it is. I just know it's positive. That's what matters here. Because a positive plus 2 is still going to be positive because you're adding something to it. Now, if you were to be subtracting 2 here, then you'd actually have to check, hey, is 3/4 times 6 going to be more than 2? Will it still keep it non-negative? That'd be our issue. But regardless, that is an answer. So now let's check -5/2, which I accidentally undid the 2 for a moment. So -5/2, if I check that here, that would make 6n negatives. So we have to check, is that bigger than 2? So as I plug this in, 6/1 times -5/2, and I do and I'm going to add 2 to that. 6/1 times 5/2, I'm going to reduce the 6 and 2 by 2 to becoming 3 and 1. And so I get -15 plus 2, which, that's -13, meaning this is 100% extraneous because it causes the absolute value to equal a negative, which is our no. Moving on to number 16, to close out absolute value equations before moving on to absolute value inequalities, I already have my absolute value by itself, and maybe I just flip it around before changing my equations to make my life a little bit easier. If you wanted to go ahead and start writing your 2 equations now, that'd be a-okay as well, of course. So I'm going to rewrite my inequalities, and I get my equations, 6w plus 20 equals the normal opposite side, which is -4w minus 2 in this case. So even though there's negatives there, that's okay. We're not concerned about that. We're going to go and solve it and see what happens at the end regardless. And our other equation makes the right side the exact opposites, where 4w becomes positive and 2 becomes positive. So as we solve each of these, the one on the left here, I'll add 4w to each side to get 10w. And then I'll subtract 20 to move it away from my variables and get -22. That results when dividing by 10 in -22/10, which reduces by 2 to become -11/5. The other inequality, I subtract 4 and get 2w. I then subtract 20 and get -18. If I divide by 2, I get w equals -9. Now, while both of these are negative, we have to check to make sure whether or not it's going to make the absolute value equal a negative, which you can check in your initial, or after we flip the sides, it doesn't matter. So as I do -11/5 times 4w, so -4 times -4, not 4w because it would replace w. Put this over 1, and that doesn't reduce, unfortunately, which is a bummer. So we get 44/5 multiplied straight across. And for a decimal, which might be helpful here, 44/5 is 8.8. And 8.8 minus 2 would be a positive. So that's an answer. Now we plug in -9, which will not require any reducing or multiplying straight across. We just do -4 times w. So let me do this off to the side here. -4 times -9 minus 2 and seeing what we get there. So -4 times -9 is positive 36, which subtracted by 2 would get 34, which is a-okay. So both here are solutions. So once again, the only time you truly have to check for extraneous solutions is when you have variables on the side opposite the absolute value after you solved for the absolute value or after you've isolated the absolute value. Because that's the only time it's possible that the absolute value could equal a negative once you plug a solution in, but not beforehand. So here, for example, the absolute value wasn't equal to negative here or here, but it did when we plugged it back in. And here, the absolute value equal to negative here, but not when we plugged either of these in. Whereas if the absolute value equals a negative beforehand, and it's just a number, not a variable, that was extraneous like we had on number 7. Now that we've covered absolute value equations, let's move on to absolute value inequalities. So absolute value inequalities, we have 2 scenarios. One is if it's a greater than or equal to, and the other one is if the absolute value is less than or equal to the other side of the inequality. And these 2 scenarios differ a fair amount in them and how we solve them and how we write them and everything going forward there. So let's first talk about the greater than or equal to. So here, the absolute value of x is greater than or equal to 7, which means the distance x is from 0 is more than 7 or equal to 7. So in order for it to be more than 7 or equal to 7, it could be at positive 7 and anywhere to the right. Any of these numbers would be 7 or further from 0. And on the other end, it could also be negative 7 or less. Once again, these would also be 7 or further from 0. Everywhere between 7 and negative 7 would be less than 7 from 0. It'd be closer than that. And so this, we might notice, looks very familiar given previous sections. This looks like a compound inequality because it actually is a compound inequality. It's really an OR compound inequality. So really what we have here is x is greater than or equal to 7, or x is less than or equal to negative 7. And as I mentioned before, some people might be sticklers as far as writing the one with the smaller number first. I am not going to be. And how we end up really getting to this point, though, as far as this and beyond, is just like before with equations, we rewrite one the exact same, where we just drop the absolute value. So x greater than or equal to, and then the opposite side of the absolute value just stays the same. Whereas the other one, we made the opposite side of the absolute value the opposite sign, in this case, negative. But we also notice we flipped the inequality symbol here. And so that's the key difference between absolute value equations and absolute value inequalities, is that when you make the second one, you also flip the inequality symbol in addition to making that opposite side of the absolute value the opposite signs. So now if we were to do the interval notation, we do them just like we would have done for OR compound inequalities, because this in reality is an OR compound inequality. It just looked different to begin with. And so, I erased too much there. So the interval notation would be negative infinity, comma, negative 7 with a bracket. Union, that U with a tail on it from before. 7, comma, infinity with 7 having a bracket again. And one thing I like to call these compound inequalities, the absolute value inequalities here for greater than or equal to, is I like to call this greater. See, because it's OR compound inequalities. Every time it's a greater than or equal to for absolute value, it's always going to be OR, okay? Whenever the absolute value is greater than or equal to a number or on the other side, it's always OR 100% of the time. Now, if it starts out this way and then something manipulates it, like you have negative 5 here and you divide and it changes this, then it no longer would be the case. And we'll get into that next case right here, talking about less than or equal to. So here, the absolute value of x is less than or equal to 4, meaning x is less than or equal to 4 away from 0. So 4 is 4 from 0, and negative 4 is also 4 from 0. And the only way to be less than 4 from 0 is to get closer, for that distance to get smaller and smaller. And so we'd be going in the middle there. And this looks like an and inequality because, well, it is an and inequality. And so what we end up doing here is we notice the interval notation is negative 4, comma 4 with brackets. And just like we learned to write and compound inequality before as one succinct inequality or one combined inequality here, or condensed, I think was a word we used previously, was negative 4, the smaller number, x in the middle, and the bigger number, 4, in that order. Smallest number, x, and the biggest number from left to right. And we just repeat this symbol, less than or equal to, less than or equal to. And we're saying x is greater than or equal to negative 4 while also being less than or equal to 4. And that's our answer for that one. Just like this would have been our answer up here, how we would write it. And one way I like to think about this is it's less than, emphasizing that and there. So we got greater and less than. Because once again, just like greater, it will always be or inequalities for absolute value. The less than will always be and compound inequalities for absolute value. And how we end up getting this left side here is we have the middle. We put the opposite of the absolute value there and rewrite this inequality. So we basically just rewrite this without the absolute value right there. And then we keep that same sign. We take the opposite side and we make it the opposite sign and put it on the left. So what does this mean? Well, as I've mentioned multiple times in here, this means that absolute value inequalities are compound inequalities. And once again, how to know which type it is and or depends on the symbol, whether it's less than or greater. So solving these, we really are going to have the same steps where we isolate the absolute value, we create the two cases, and here it talks about the KISS method, which is a neat way to remember it. So you keep it, switch, which basically just means that for this first one, you keep the variable or what's inside the absolute value, you switch the inequality symbol, and you switch the signs of the opposite side. So you keep it, you switch it, and you switch. Or keep it, switch, and the it is the I for KISS. So keep it, switch is what it's talking about there. And then solve both inequalities and graph your solutions writing in interval notation. Now I do want to note you could do that KISS or the keep it, switch for this as well, and then condense it afterwards. So what you could do is, x is less than or equal to 4, write that normal, and the other one, keep what's inside the absolute value, switch the inequality symbol, and switch the opposite side to the opposite signs, and then just write these next to each other. Once again, the smaller number, flip the sign, variable in the middle, and we just rewrite that part. So however you think about going about those less than ones is fine. I prefer doing it this way because then we already have it written how we like and inequalities written. And then we graph these and write our answers in interval notation, especially when we're asked. Basically, just do what's asked at that part of the end of the problem. So if they're asked for interval notation, we do interval notation. If we're asked for set notation, we do set notation. If we're asked for blank, we do blank. So solve, graph, and write each solution in interval notation. So number 1, the absolute value of x plus 6 is greater than 7. So this is a greater, I'm noticing, and the absolute value is by itself. So I'm going to go ahead and make my two cases, one where everything's the same, and the other where I switch the inequality symbol, and I make the opposite side negative, or the opposite signs. My pencil wigged out there. And I solve each of these inequalities separately using the word or between it, because once again, that's greater. And I subtract 6 from both sides, and I get x is greater than 1. Subtract 6 from both sides, and get x is less than negative 13. So I have x is greater than 1, or x is less than negative 13 as our answers. And so I go and do an open circle at 13, it goes to the left, an open circle at 1, and it goes to the right. The nice part here is, since we use the same symbol, but just flip it, is that they'll either both be open circles or they'll both be closed circles. And when it comes time for interval notation, which we'll do here, they'll either both be parentheses or both be brackets for the numbers we're using. So here for the interval notation, it'd be negative infinity, comma, negative 13 with parentheses, union, that u without a tail, 1, comma, infinity with, once again, parentheses. Number 2, the absolute value is by itself, and we have less than, which means it's less than. So I'm going to rewrite the middle and rewrite this. And then on the opposite side here, I'm going to make this an and inequality and do that same symbol, the less than symbol, again, like we did a moment ago, and just make this opposite side negative. Now, as I look to solve this, we solve this the same way we would have solved condensed and inequalities before, where we add 3 to all 3 parts. And I end up getting negative 16 is less than 2v, which is less than 22. I then divide everything by 2, and I get v compared to 11 on the right and negative 8 on the left. And now I solved it. So I'll go ahead and graph it. Negative 8 is an open circle. 11 is also an open circle. Oops, see, that'd be 10. So 11 would be in the middle there, because this is going up by 2s, I notice. That's always an option here on a graph, by the way. If you aren't given the numbers and you're like, oh, these numbers are far apart, you could always go by 2s or some other interval if you'd like. That's something available to you. So the interval notation would be between 8 and 11, with both being parentheses. Number 3, the absolute value of negative 5 plus k over 3 is greater than or equal to 1. So this is greater than. So we're going to have or, two separate inequalities that we just graphed together. So I'm going to write the first one, which everything stays the same except for the absolute value of r's are gone. The second one where we flip the inequality symbol and to make the opposite side negative. So in both of these, I'm going to worry about adding the 5 first, since only the variable is being divided by 3. If the whole thing was divided by 3, I would undo the division first. So adding by 5 gets me k over 3 is greater than or equal to 6. And then multiplying by 3 gives me k is greater than or equal to 18. In my other one, I'm going to once again add the 5 first, and so I get k over 3 is less than or equal to negative, so it's going to be positive 4. And then multiplying by 3 on both sides gives me k is less than or equal to 12. And so it's this or that as I box my answer, and I turn to graphing it here. So I have less than or equal to 12, so 12 when going left, greater than or equal to 18, so 18 going to the right. The interval notation here would be negative infinity, comma 12 with a bracket, union, and 18, comma infinity with a bracket. Number 4 here, absolute value of 7 minus 4n is less than or equal to 27. So this is an and one. So I'm going to rewrite my middle, make it less than or equal to 27, make it less than or greater than or equal to, as we make a less than or equal to symbol, just keep the same symbol, negative 27. I said greater than or equal to because the central part is greater than or equal to negative 27, even though this is a less than or equal symbol. Now I worry about getting my n by itself by subtracting 7 first to all 3 parts. And I get negative 34 is less than or equal to negative 4n, which is less than or equal to 20. Dividing by negative 4 on absolutely everything. I'm going to have n. I'm going to have this reduced to 17 over 2, or just calling this 8.5. And I'm going to have this be negative 5. And because I divided everything by negative, I flipped these inequality symbols. However, I do want the smaller number on the left and the bigger number on the right to mirror my interval notation and the graph. So I'm going to have negative 5, n, and 8.5. And because I flipped the entire inequality around, I flipped these symbols once again. And that would be my answer. So I close dot on negative 5, close dot on 8.5, and I connect the two. Interval notation would be negative 5, comma 8.5 with brackets. Now you may be wondering, are we going to have special cases with these absolute value inequalities? We've had special cases with our compound inequalities. And the answer is kind of, but not really. It'd be basically the same as our special cases for absolute value equations. Basically, when the absolute value equation was equal to 0, you had one solution. And so the same thing may be true for absolute value inequalities, which we can see like, hey, if this was less than 0, okay, would be similar to saying this is less than negative 5. Because is it possible that distance is ever less than 0? No, so that would be no solution. Is it possible distance could ever be less than negative 5? No, so that's no solution. Whereas our greater than numbers, such as we see on number 1, if I were to put greater than negative 2, well, distance will always be greater than a negative number, any negative number for that matter, and so that would be IMS. Whereas if I put greater than 0, well, there's a lot of different ways it could be greater than 0, but it's not 100% of ways, because there is one way that it's just at 0, so we'd actually have to solve that. Whereas if it's greater than or equal to, it just wigged out there, my apologies. If it's greater than or equal to 0, distance will 100% of the time either be equal to 0 or more than 0, because that's every non-negative possibility. So with these absolute value inequalities, we don't necessarily have the special cases where we have to pick which graph we're going to deal with, or say we have an and going apart where it should be going in, or an or going together, where it should be going apart, and all those different things. You don't have to worry about that. We just have to worry about the absolute value comparing to negatives and zeros in certain scenarios, and be careful with that. And when I say comparing to zeros in certain scenarios, I'm talking about the greater than 0 versus greater than or equal to 0 being a difference there. Moving on to our last page, we notice here on this last page the problems get a little more complex where the absolute value is not entirely by itself. So the only thing that changes here is we first have to get the absolute value by itself, and then we continue on with what we did on the first 4 examples of this section. So here we undo the division of 5 by multiplying by 5. And we get the absolute value of q minus 3 is greater than or equal to 5. And so this is an OR compound inequality since it's greater. So I'm going to rewrite these two inequalities just as I did on the previous 4 problems. And start solving them by adding 3 and get q is greater than or equal to 8, or q is less than or equal to negative 2. Graphing those would give me negative 2 for a closed circle going left, 8 for a closed circle going right, and the interval notation would be negative infinity comma negative 2 with a bracket, union 8 comma infinity with a bracket again. Number 6, I'm going to have to subtract 3 first to get my absolute value by itself, so I get the absolute value of 8a plus 10 is less than 22. So this is a less than, so I'm going to drop my absolute value bars, and then add in the negative 22, which is less than the center of this compound inequality. So now as I subtract 10 from each part of this, all 3 parts, I get negative 32 is less than 8a, which is less than 12. And if I divide everything by 8, I get negative 4 on the left side, and 12 over 8 reduces or becomes the reduces to 3 over 2, I should say, or becomes a decimal 1.5. Either way you word that, or the mixed number 1.5 is fine. So I'm going to put negative 4 as an open circle, 1.5 as an open circle, and connect the 2 since it's and. In my interval notation would reflect it as well as negative 4 comma 1.5 with parentheses. I do want to note, I often prefer fractions, especially improper fractions, over decimals. That's just my personal preference. Except for when we're graphing. When we're graphing, I find decimals to be far easier to get visual examples and to count with. But otherwise, I much prefer the improper fractions because I find them to be easier for me to do and a little bit lazier. That's my personal preference. But once again, I'm not specifying what you need to do, and so unless I do specify on a certain problem and it says very specifically I want it in this form, I really don't care as long as you round appropriately or use repeating bars. So like, make sure to call 2/3 0.6 repeating as opposed to like 0.6 or 0.7. Number 7 here, I'm going to have to undo this multiplication of negative 10 by dividing by negative 10. And we may notice that, hey, since we're dividing both sides by a negative, that we're going to have to flip this inequality. So what started as a less than is actually a greater. And so now as I make these two different inequalities for my greater, it results in those. And as I start solving, I add 1 to both parts of the inequality and get 7. Or I add 1 to both parts of the inequality. Oop, I forgot to write the plus 1 here, so let me write that in. And I get negative 5. Then from there, I divide by 2. And I get 7 over 2, or 3.5, or 3.5. And I get negative 5 over 2, or negative 2.5, or negative 2.5, whatever you prefer out of those scenarios. And it's this or the other one for my solutions. So as I go ahead and graph these here, negative 2.5 closed circle going left, 3.5 closed circle going right, with it being interval notation of negative infinity comma negative 2.5 with the bracket, union, 3.5 with the bracket, comma infinity. Number 8, we have to add 5 and then divide by 9. If you wanted to divide by 9 first, you just have to divide every part by 9, which gets quite messy here, and maybe it'll get cleaner if we add 5 first. Maybe that number will be divisible by 9, and guess what? It will be, because adding 5 to both sides results in 72 on that right-hand side. So now as I divide by 9, I can do 72 divided by 9 without making it a fraction or decimal, which is something I'm quite thankful for, and get the absolute value of 3 minus k is greater than or equal to 8. So greater, I'm going to have two different separate inequalities. And I begin solving this. I'm going to go ahead and subtract 3 from both sides and get negative k is greater than or equal to 5. And then I'm going to have to undo that negative, so you can multiply or divide by negative 1, and get k is less than or equal to negative 5. Working on the other inequality, I'm going to subtract 3 and get negative k is less than or equal to negative 11. And then I'm going to divide by negative 1 and get k is greater than or equal to 11. And you might wonder, well, we switch these inequalities. Is that going to affect it to now it's an and 1 compared to an or 1? And I'll tell you the answer is no. Since it started out as an or 1, once we split it, it's going to continue to be an or 1. And if we look at the graph, we'll see that's the case. So if I go to negative 5 and make my closed circle, and I go to the left, because that's what it's saying to do, less than or equal to, and I go to 11, make an closed circle, and I go to the right, we notice this is, in fact, an or graph. So my interval notation would be negative infinity, comma, negative 5 with a bracket on negative 5, union, 11, comma, infinity with a bracket on the 11. Number 9 here, we have to subtract 7 to start on this problem. So we have 6 times the absolute value of negative 5n is greater than 30. Then I divide by 6 and get the absolute value of negative 5n is greater than 5. So now I drop the absolute value and I get negative 5n is greater than 5, or negative 5n is less than negative 5. Solving these results in dividing by negative 5 and getting n is less than negative 1, and dividing by negative 5 again and getting n is greater than positive 1. And those are my two scenarios. And so I go ahead and graph them, less than negative 1 and greater than positive 1. So the only part that's not a solution is between negative 1 and 1, including negative 1 and 1 themselves. The interval notation here would be negative infinity, comma, negative 1 with the parentheses, union, 1, comma, infinity, with the parentheses as well. I just want to clarify this, negative 1, my negative was quite close to my 1 there. Number 10 here, in order to get my absolute value by itself, I first have to deal with this positive 1 by adding 1, or excuse me, this negative 1 by adding 1. And so we have, as my iPad glitches on me, negative 4 times the absolute value of x plus 9 is less than or equal to negative 20. Dividing by negative 4, the absolute value of x plus 9 is greater than or equal to 5. So notice this switch to a greater than, and it just happens to be that the majority we've done so far is greater than or equal to, as compared to less thans. That won't be like necessarily a consistent trend in problems where it's like, oh, most of the problems are always this. It just happens to be in these examples. X plus 9 is greater than or equal to 5, or x plus 9 is less than or equal to negative 5. Solving by subtracting 9 from both sides is x is greater than or equal to negative 4, or x is less than or equal to negative 14. So we graph those. Negative 14, closed circle going left. Negative 4, closed circle going right. And the interval notation is negative infinity, comma, negative 14 with a bracket by negative 14, union, negative 4 with a bracket, comma, infinity. Number 11 here, we have to add 9 to undo this absolute value, or to get the absolute value by itself. So 3 times the absolute value of 8x plus 5 is greater than or equal to 33. Divide both sides by 3, and the absolute value of 8x plus 5 is greater than or equal to 11. So it's another greater than or. So we have 8x plus 5 is greater than or equal to 11, or 8x plus 5 is less than or equal to negative 11. Subtracting by 5 on both sides gives us 8x is greater than or equal to 6. Dividing by 8. I meant to switch colors there for a new step. Dividing by 8 results in the reduced fraction of 3/4, or the decimal 0.75. The other one, subtracting 5, gives me x is less than or equal to negative 16, and dividing by 8 results in the integer x is less than or equal to negative 2. So this or the other one. And graphing these, negative 2 is a closed circle going left, negative or positive 0.75, about 3/4 of the way from 0 to 1. Doesn't have to be perfect. I'm not pulling out a ruler to check how far along it is to make sure it's exactly 3/4 of the way. So now our interval notation would be negative infinity, comma, negative 2 with a bracket, union, 0.75, comma, infinity with a bracket around 0.75. Last but not least, I'm going to add 9 here to get 4 times the absolute value of 9 minus 3n is less than 84. Then we'll divide both sides by 4 and get the absolute value of 9 minus 3n is less than 21. And so we finally have a less than scenario again. It's where we keep the middle the same, we keep the right hand part the same, and we just write negative version of the opposite side of the absolute value and put another less than symbol to match. And now we solve this one by subtracting 9 from all 3 parts. And we get negative 30 is less than negative 3n, which is less than 12. And unfortunately, this is a negative, so meaning when we divide by it, we'll be flipping these inequality symbols. And I say unfortunately because that's going to require another step in a moment to flip them back. So we have 10 is greater than n, which is greater than negative 4. And we want our smaller number on the left, like I mentioned, so we have to flip it around again. So negative 4 is less than n, which is less than 10 is our answer. And so we do an open circle at negative 4, an open circle at 10, and we connect the two. And our interval notation is negative 4, comma 10 with parentheses. And that finishes up section 1.5, which also finishes up Algebra 2, Unit 1.